How many of you here have an Alexa Echo or your hands? Any kind of Amazon product? So the next speaker is going to speak is Nikko Ström, is the senior principal scientist at Alexa, founding team in the Echo team. Has over 20 years of experience in automatic speech recognition, and has spent some time at Microsoft, at MIT, prior to his time at Amazon. So we'll now look at voice with a very different embodiment, one in the form of something like an Alexa Echo.
Thanks. Testing, is it working? It's working, great. Oh, I need the clicker. All right, so I'm Nikko Ström. I work in the Alexa machine learning team. So we built, so it's weird. A year ago or so, I had to explain what this thing was. No one knew what it was, and I had to take some time to explain. Now, let me just say this is the Amazon Echo, and our team built it, and it's powered by Alexa, which is the voice service. And it's this device that you put in your house, in your room, and you can talk to it from over there. And it doesn't really come with a remote. So when you use it, you use speech to use it. That's the only way you use it. And thanks for Adam and Lee for the talks earlier. They were really interesting. I'm going to make some of the same points as Adam. I'm sorry about that. I didn't know his talk. And Lee, you brought me back. It was interesting. I was also working on that MIT system back in the day. And what he didn't tell you was that it took several minutes for each dialogue turn. Like, so you would say, are there any tickets to San Francisco today? And then you'd wait 2 minutes, and it would respond. And it had this annoying Jeopardy music playing when you were waiting, too. So it was really super annoying. And then it would come back and say, I'm sorry, I didn't understand that. Anyway, so this family of devices grew. We built this smaller dot. I have several of those in my house because I use this for lighting, right? So I need one in each room. So I need to say, turn on the lights, and it would turn on the lights in that room. And then, of course, we have a couple of other devices. This is a tap. It is not plugged into the wall, so you can take it with you. And then this year, for the holiday season, we added just a different color, white for the dot and the Echo. I thought I'd show this here, because I know here in Silicon Valley, you like your electronics to be white. Anyway, so also there are other devices. It also powers the Fire TV, is Amazon's set-top box. It's now on our Fire TV tablets. You can use it there. And then there are also third-party devices that use Alexa. So we have this API called Alexa Voice Services, where you can, any device maker can connect to Alexa and get that same experience. I actually have the co-watch on me today, so if you want a demo, I can show you after. Other devices that don't really have Alexa built in, but they connect to the same system are a lot of the lighting, the smart lighting products. Almost all the major systems are connected to Alexa, so you can use it. You can just say, turn on the lights in the living room, and so on. There are some smart ovens. You can preheat your oven. There are ranges and coffee makers. You can tell it to make coffee, and of course, thermostats. Skills are how third-party developers add new experiences to Alexa. Here are some of the skills. There are thousands of them that are certified that users can install on their system. So all of this growth in different directions, skills, many different devices, and so on. By the way, in terms of growth, so we started out small 2 years ago with a beta program, and then we made it available generally, and we sold several million of these. And I'm hearing that this holiday season we sold more than ever again. So you have to think about this as something that, which is, there are millions of these out in households, and they're not collecting dust. People are using them a lot, and the only way you can use it is with speech. So what this means is that we get lots, really an insane amount of data coming into us, speech data that we can record and we can work on. And so that leads me to a challenge and an opportunity. We have more data than you can imagine. Unfortunately, they don't let me tell you how much data we have, but just think about a really big number. By the way, so I'm going to talk about some how we scale deep learning. And there's a longer form talk that I did at the reInvent conference last year. It has the same title. So if you want more of this, if you want more of me, I'm at YouTube. Anyway, so about how much data we have. So if you're, and this is where I'm going to make some of the same points as Adam. If you're 16 years old in the US, you can drive a car, and you're very proficient at English at that point, right? So that's 140,000 hours. But you probably don't hear speech all the time. Maybe you hear speech 10% of the time. I don't know. But that's about on the order of magnitude of 14,000 hours of speech. You've heard that in 16 years, right? So let's keep that number in mind for perspective when we look at these other things. So we have all these thousands of hours of speech stored from our users, and we have transcribed them so we know what the correct words are. And we need to train our deep learning models. And so we do that on AWS, on the GPU instances that are there. And because the scale of this, we have to distribute these over many, many GPUs, right? There's a big challenge with that because the learning algorithms, they're difficult to scale for distributed training. All nodes generally tend to communicate updates to this model with all the other nodes all the time, several times per second. And so you get this quadratic problem, and you get to the I/O bottleneck. So there are many different types of solutions to this problem. The one that we came up with is based on some approximations and some compression of these updates to make them much smaller. So several orders of magnitude less data that you have to communicate between the nodes. Anyway, so here's a paper from 2015 that we published about this. The x-axis is the number of GPU nodes that we use. So in this case, we used up to 80, and we varied that. And then on the y-axis, you see how fast, what's the throughput, essentially, of the speech. So the key point here is that the line is almost linear. So it scales very well for distributed training. One more thing that I want to say about this is that, so if you look at the number 80 there, we used 80 GPUs, and it's about 550,000 frames per second. That corresponds to processing about 90 minutes of recorded speech every second. So 1.5 hours of speech we process every second. So if you remember that 16-year-old had heard 14,000 hours of speech, this system can process this in about 3 hours. And then it can process it again in 3 hours, and again. So I mean, we're talking about, how fascinating it is that these systems can actually reach human parity. We better reach human parity when we have these resources, right? We have much more resources than that 16-year-old had to learn speech. So now I'm going to quickly just talk about a few applications for deep learning. We use it almost everywhere in the Alexa system. So. But one of the first one was speech recognition, obviously. And Adam had a different graph of speech recognition here. I really like that system. But here's how most of the current state-of-the-art systems are factored. You have a first step, which is the signal processing. And out of that comes the feature vectors. That's essentially the spectrogram that he showed you. And that is followed by an acoustic model. Out of the acoustic model comes some classification of what is this speech. Every 10 milliseconds, what is this speech? What's the phonetic class of this speech? That is followed by a decoder, which has information about all the possible pronunciations of words and all the phrases that users use and the grammar that they use and so on. And out of that system comes some raw words. And then there's usually some text post-processing to clean up the output to get a nicer text. So that's how it typically works. It's a vanilla system. Like I said, we're using machine learning and deep learning in all these blocks, but I'm going to talk mostly about the acoustic model here, just a little bit more about the acoustic model. Because one interesting thing about these deep models is transfer learning. So Jeff talked about that this morning, how that's used a lot in computer vision and object recognition. It can be used in speech recognition too. So let's say we have this, so this thing represents the spectrogram. This is the input to our system. And then we have some deep neural networks, typically much more complicated than this, but some hidden state. And then the output layer of phonetic symbols, right? So we've collected, like I said, a very large amount of speech for US English. And so we trained this model using that, right? And now we have a very well-trained acoustic model for US English. But it doesn't end there, because this year we launched Alexa in Germany as well, right? So now we have to build a system for German. What you can do is you can just remove that one last layer and keep the rest of the networks exactly the same. Add a new layer for German that has different phonemes, because German is a different language, it has different phonemes. Initialize that new layer just randomly, and then train with whatever data we have for the German language. And it turns out that when you do this, you get a very good system, much better than what you would get if you trained the system from scratch with only the German data. And we can speculate that that is because there are so many things in language that's the same. And our system is a far-field system, so it has to learn about room reverberation, and that is the same in Germany and US, I think, mostly. So that's one very, very powerful thing about these deep learning methods. How much time do I have left? Anyone?
2 minutes.
5? OK, so I want to talk about another problem that we're solving with deep learning, the cocktail party problem. So in the middle there is an echo. It needs to listen. So there's many people in the room. It needs to figure out who's talking to it, right? The start of the speech is pretty easy, because there's this wake word. So you say, Alexa, and then it understands that, OK, I should probably listen in that direction. There's a microphone array on this thing, so it can direct the listening in one direction. The rest is much harder, right? You can barely see which one is directed to Alexa here. And you can't really know when they're stopping. So if two people are close to each other, it's going to listen in that same direction. And you don't really know when the speech of the one person stops if the other person keeps talking, right? That's a hard problem to solve. And so the way we've worked on solving that is this. So let's look again at this. Alexa, play some jazz. There's a wake word, and there's the actual request. And we call the wake word the anchor, and then the rest should be consistent with the anchor, right? There should be the same type of voice. It's the same person. So we solved that again with an encoder-decoder neural network architecture. Jeff talked about that earlier today also. And so here's some more detail on that. So first, we get the Alexa wake word. We use a recurrent neural network to extract an embedding from that. So we get the speech features, and then in that embedding represent the characteristics of the voice, essentially, right? Now, the next part of the utterance is processed by a different recurrent neural network. And it'll get the input both from the embedding and from the features of the speech, the spectrogram. And based on that, it'll make its endpoint decision. So the embedding will help it know when it's no longer the same speaker talking, right? So that's how we solved this cocktail problem. And that was a paper we published last year. Real quick, I'm going to talk about how we use deep learning in speech synthesis also. The basic steps of speech synthesis is, text normalization, and then convert it to phonemes, the words to phonemes, and then comes the big step, which is the hardest one, which is how do you generate the waveform out of that.
She has $20 in her pocket.
And then it'll sound something like that, right? The way we do that, and most of the high-end systems do that, is using diphone unit selection, and that's based on recording a large database of diphones, the beginning of one phoneme and the end of the next. And then having an algorithm for finding the best sequence of connecting these diphones together. To do that, you have to have an objective function, and this is done by, so we annotate each of these segments with some attributes like the duration, how long is it, what's the pitch of that particular segment, and what's the intensity or level of speech, for example, and a lot of other things. And so what we've done with deep learning here is that we use a recurrent network to come up with good target values for each of these segments, for pitch, duration, and intensity. And the input to that network are features that we can get from the text, right? So now we use those target values to search the big database of small speech segments. And that is one of the inputs to the algorithm that finds the correct sequence to stitch together. And so I'm going to play the before and after now. And you have to listen carefully because the baseline is pretty good too. But I think you'll hear that it flows better after we use this.
Over a lunch of Diet Cokes and lobster salad one balmy fall day in Boston, Joseph Martin, the genial, white-haired, former dean of Harvard Medical School, told me how many hours of pain education Harvard med students get during 4 years of medical school.
All right, that was with the rule-based system for finding the correct pitch and duration. Here's after we use the deep neural networks, and try to remember what you heard before.
Over a lunch of Diet Cokes and lobster salad one balmy fall day in Boston, Joseph Martin, the genial, white-haired, former dean of Harvard Medical School, told me how many hours of pain education Harvard med students get during 4 years of medical school.
All right, I don't know if you could hear that, but it does flow a little bit better. And this is all I wanted to show you today, and I think my time is up, so thank you very much.